Hello everyone, my name is Salman Bawa, and today the topic of my presentation is At the Junction. We will begin by exploring how a junction forms and what are the types of junctions. We will then look at the charge, the field, and the potential at the junction, and have a look at the band diagram of a PN junction in a simple Excel graphical calculator. We will then cover the complexities and considerations that we need to make when we are dealing with heterojunctions and the summary of the presentation. So why are junctions so important? Well, without the junction, we would not have diodes and our transistors, LEDs, and we would not even have solar cells without junctions, whether those be crystalline solar cells, thin film solar cells, or multi-junction solar cells. So the formation of a junction leads to the several products listed here on this slide. So how does a junction form in a semiconductor? Well, it forms because of a change. That change could be abrupt, steep, or gradual. The change is in either the doping of the semiconductor or the material of the semiconductor. So let us look at doping. We could dope the semiconductor p-type on one side and n-type on the other side, which means that the carrier concentrations would be different on each side of the semiconductor. So as the carriers flow at the center of the semiconductor, we would have a region where the carriers cross over. And when that happens, it leads to fixed ions, and it is depleted of the mobile carriers. This depletion region forms the width of the junction. And obviously it would be P side on one side of the junction and N side on the other side of the junction. And because of these fixed ions, we have a charge density developed at the junction that causes the electric field, that causes the potential, and hence the energy band diagrams. Another way of forming the junction is to use a different material, which means that two different materials, completely different materials, could join together. And when that happens, we have to consider the intrinsic carrier concentrations of the two different materials. The electron affinities of these materials with respect to the vacuum level. The width of the junction would depend on the type of the material that we are using, and the relative permittivity of that material would play a role in the width of the junction. So the width in material 1 could be very different from the width of the junction in the material 2. But because of this difference in material, and at the junction, we have fixed ions formed. So there'll be a charge density. There'll be an electric field, which would cause potential, and then the energy band diagrams. A junction has many names. It's called a junction. It's also called a depletion region, space charge region, and in case of solar cells, we hear the word tandem solar cells. But there are two types of junction. One is a homojunction. As the name suggests, this is the same material, and so the only way to form a homojunction is via doping. And the doping could be different on each side, an N-type and a P-type, and so we'll form a junction. The other way to form a junction on another type of junction is heterojunction. In case of heterojunction, the materials are different, and these are formed using epitaxial growth methods. So one material could grow on top of another material to form the junction. So what are the contents of a junction? If we explore carefully, once we form a PN junction, the mobile carriers would travel close to the junction, cross over, and form fixed ions. These fixed ions form on the P side and the N side. And this is the formation of the junction. There's a density of negative charges on the P side and a density of positive charges on the N side. And these charge densities form an electric field that results in a potential or a built-in voltage. And all this leads to the very important energy band diagram. This band diagram shows the energy levels of the valence band and the conduction band and the Fermi level in the PN junction. And we know that it is because of this that we have a built-in voltage, and so we need a certain voltage that has to be applied to the PN junction to forward bias. And when we forward bias, the QV0 that you see on the slide decreases. And if we reverse bias, the QV0 on the slide increases, making it difficult for the carriers to move in the junction or across the junction. So the energy diagram is very important in understanding the function and the operation of a junction. In fact, Herbert Kromer said that if in discussing a semiconductor problem, you cannot draw an energy band diagram, this shows that you don't know what you're talking about. If you can draw one, but you don't, then your audience won't know what you're talking about. So the energy band diagram is extremely important. So let us explore the role played by each of the contents of a junction. When we dope a semiconductor p-type on one side and n-type on the other side, there is a carrier concentration gradient that forms. And because of this, the carriers diffuse towards each other. At the point where they meet, they cross over and recombine. Once that happens, the region where the recombination occurs is left with fixed ions. These are positive donor ions, N sub D on the N side, and negative acceptor ions, N sub A on the P side. And so there is a charge concentration represented by rho of x, which is equal to Q, which is the charge, 1.6 times 10 power minus 19 times N sub D, coulombs per centimeter cube on the N side, and the charge density is minus Q N sub A, coulombs per centimeter cube on the P side. These charges cause an electric field, which is the integral of the charges or the charge density divided by the relative permittivity of the semiconductor in volts per centimeter. The integral of the electric field provides us the potential, and Q, which is the charge, 1.6 times 10 power minus 19 times the voltage, provides us the energy. We could express this energy in electron volts. Let us look at these contents of a junction in a bit more detail. So rho of x, which is the charge density, equals Qn sub d minus Qn sub a. This is assuming that the n side is on the left and the p side is on the right of the junction. And the integral of the charge density divided by the permittivity of the semiconductor is the electric field. So once we put the expression of rho of x, we get the electric field equals 1 divided by the permittivity of the semiconductor times the integral of Qn sub d minus the integral of Qn sub a. We are assuming that this junction is abrupt, which means that at x equals 0, that's where on the left of x equals 0 is the n side, on the right is the p side. Now we'll have to put the limits on the integral, and these limits would represent the width of the junction. And since n-type is on the left side and p-type is on the right side of the junction, which is at x equals 0, our integral limits turn out to be from minus x sub n to 0, which is to the junction, for q times n sub d. And the limits are from 0, which is at the junction, to xp, which is the width of the depletion region on the p side, for q times n sub a. And we know that there will be no n sub a on the n side, and there would be no n sub d on the p side. So after we integrate and apply the limits, we get the second last expression on this slide, which is 1 divided by the permittivity of the semiconductor times q n sub d x sub n minus q n sub a x sub p. And if we want to express this expression in terms of x, which is at any point of the junction, we get the last expression on this slide. So the electric field at any point in the depletion region, which is x, equals 1 divided by the permittivity of the semiconductor times this expression, the last expression on this slide. Okay, so the integral of the electric field, which is the first expression on this slide, is the potential. And the expression of the potential that you see on this slide, which is V of x, is in fact the built-in potential, or V naught. And V naught times Q equals the energy, E of x, which is the last expression on this slide. So the junction, or the depletion region, has a width W sub j, and this runs from minus x sub n on the left side to x sub p on the right side. So the width of the junction is given by the expression x sub p plus x sub n, which is equal to the expression of the W naught on this side. And the width of the depletion region on the P side, x sub P, is given by the expression that you see on this slide. And the width of the depletion region on the N side, x sub N, is given by the expression that you see on this slide. Okay, so we have gone over a number of expressions in the previous slides, and we want to use those expressions in a simple Excel graphical calculator that empowers the user to choose the left side and the right side of a p-n junction as either n-type or p-type, put in some values for the doping concentrations on each side, n sub A and n sub D, that would lead to the charges, and then the electric field and the potential, and this would all be reflected in the energy band diagram. At the same time, we want to empower the user to choose the material characteristics such as the intrinsic carrier concentration, the density of states at the conduction band and the valence bands, the electron affinities from the vacuum level, the band gap of the semiconductor, and the relative permittivity of the semiconductor of the user's choice. So it's time to have a look at our very simple Excel graphical calculator. So we will go to our Excel sheet and run some simulations.